Good morning, everybody. So today, lesson 3. It's Thursday morning, and today's lesson is 3 things. We're going to do a quick review, and then we are going to do a little lab online, and then finish off with varying the reference half cell. And then tomorrow, you guys will have an assignment and a quiz based on the first 3 days. So this is a bit of a review for you. This is a lead nitric acid cell, and in your study guide, it also says, so it says lead 2, carbon nitric acid cell, and this is page 224 in your guide. So they give you a little more information. They mention that it's got carbon in it, and the carbon is the inert electrode, right? When you see carbon, that means inert electrode. Why do we have an inert electrode? Which of these would need an inert electrode, lead or nitric acid? And the answer would be nitric acid because it has no metal. So we'll just arbitrarily call this one lead, and this one is carbon. So there's our inert electrode. So that means this is the nitric acid, HNO3. Or H plus NO3 minus. That's what it really looks like. As major entities present in water. And on the lead side, as it says in your study guide, it's lead 2. So Pb2 plus, and it doesn't tell us the anion. So we could use any spectator. Nitrate's a good one. PbNO3 minus, aqueous. So we've got our half cell labeled, both our half cells labeled. Okay. Who's our oxidizing agent, who's our reducing agent. So you go and look them up, and you discover that these guys together are a very strong oxidizing agent, and the lead solid is our strongest reducing agent. So writing out their half reactions from the data book, we've got nitric acid, 2NO3 minus and 4H plus. Oh, let's go back to that. Plus 4H plus 2 electrons gives us N2O4 gas and 2 water. Okay, and these are aqueous. I don't have much space here. Aqueous. Okay, so there's our strongest oxidizing agent. Gaining electrons and undergoing reduction. Is that going to be the cathode or the anode? Cathode. Positive. Okay, and our oxidation is our reducing agent, losing electrons. Oxidation, which becomes the anode. That's our lead solid. If you look up its half reaction, it loses 2 electrons to become lead 2 plus. Okay, net reaction, so we could add those together. I'm not going to do that. It's straightforward because the electrons are already balanced. Is it spontaneous? Yes. Oxidizing agent is above the reducing agent. If I wanted to calculate the cell potential, I could do that as well. Our cathode, the nitric acid, is positive 0.80 volts minus the anode, lead solid, and lead solid is negative 0.13 volts. Negative minus a negative becomes a positive. So something else you should know is if it is spontaneous, then the electric cell potential is always positive. So a positive cell potential means spontaneous. Okay, which way do the electrons flow in here? Towards the cathode. Strongest oxidizing agent gains them. And in our salt bridge, cations to the cathode and anions to the anode. Negative. So when you think about it, the electrons are being repelled, pushed away from the negative, and that's making this side more positive. And because it's losing negatives and getting more positive, it needs more negatives. Anions to the anode to replace the negatives that are being lost. And this side is gaining the negatives, so it needs to gain the positives to balance out and maintain neutrality to keep both sides neutral. Okay, so that's a bit of a review of an inert electrode in a voltaic cell. Now, we did all this, right? Cathode, anode, direction of electron flow. We didn't label the salt bridge. SB, salt bridge. So for our lab today, first one, woohoo, we normally do this one out in the lab and we do a whole bunch of metals. And then we try and determine, we hook them up to voltmeters and determine the electric cell potential. That would be the actual value. But before we do that, we predict them using our data book. So we're going to do the lab online. There's a simulation that you can use. Now, in your data book, in your study guide on page 272, you have this lab. I had to modify it because the one online doesn't use the same metals. So ignore in your study guide the metal combinations that they've given you, and you're going to use these ones instead. Okay, use those instead. What a mess. 2, 4, 6. And so there are 6 possible combinations that you can use to replace the 6 that we normally use in our high school lab. So how does this work? Okay, you're going to try out 6 combinations. So the one that we're going to do together first is this guy, copper and zinc. So you need to go and figure out who is the cathode and who is the anode for every possible combination. So we'll do them one at a time. So let's look up copper and zinc. Okay, so from your data book, here's the copper 2 plus copper, and here's the zinc 2 plus zinc. So hopefully it's obvious to you that this is our strongest oxidizing agent. So that becomes the cathode. And this is our strongest reducing agent. So that becomes the anode. So we got a copper cell and a zinc cell, and the copper half cell is the cathode and the zinc half cell is the anode. Okay. So we already have this one in the right spot. The copper 2 plus half cell is the cathode, and the zinc 2 plus is the anode. Okay, so we're going to assume that everything in here is sulfate for the anions. So lead sulfate, lithium sulfate, zinc sulfate, silver sulfate. Okay, predicted cell potential of a copper zinc cell. So we go back to the table and we go, the cell potential is cathode minus anode. 0.34 volts minus negative 0.76 volts, which is positive 1.10 volts. So we are predicting positive 1.10 volts. So in the lab online, you're going to go and do this combination and then record the actual voltage. So we're going to do the first one together. So I'm going to provide the link for this. It's called CK12 batteries. And so I have a battery here with a flashlight. So here's our voltaic cell. And this one is, I think it starts out with zinc and platinum. So we've got zinc in the center as our cathode, and then platinum is the anode around the perimeter. We're going to change it to copper. There's our red-brown copper, so you can see the copper here. So we've got zinc and copper. There are 2 half cells separated by a porous barrier, porous boundary, and then we have our one electrode and our second electrode right here, positive, negative. So this is our cathode, and here's our anode. Okay, so what we do is push play, and it shows the electrons flowing from the anode, your reducing agent losing electrons, to the cathode, the oxidizing agent that is gaining the electrons. So you can see the copper 2 plus is turning into copper. 2 plus turns into copper. And the zinc turns into zinc 2 plus. Okay, sorry, zinc turns into zinc 2 plus, and the copper 2 plus turns into copper. And we have our reaction down here. Now, what we're interested in is cell potential, and here's our graph. So we predicted 1.10, and if you look at the graph up here, it is, we're going to have to estimate, looks like about 1.1. I'd say that's a tenth of the way. So 1.1, back to our chart. 1, I'm guessing on this digit, so I can only go to one decimal place, 1.1 volts. So that one worked as predicted. You guys need to write out and try the other 5 combos that are left, doing the same thing I did. Which one is cathode? Which one is anode? Go to the battery, change it. So let's say zinc silver was my next one. There it is. And then I will push play and run it and record the voltage. And as you're doing this, like, try and understand this battery and this flashlight. How is it working? Cathode, anode, flow of electrons, flow of ions. Hopefully that practical example helps you to understand these a little better. So if you would like to stop now and go and do that lab on page 272, you could do that. And then come back to the lesson. There's just one small topic left, or you can save that and finish off the lesson in your notes, in your study guide. That's up to you. Okay, so our main topic for today is talking about the standard hydrogen half cell and then varying the reference half cell. What the heck does that mean? So I'm going to back up for a second. You may have noticed already that hydrogen is assigned a value of 0 for its cell potential. Here it is. So what they've done is they've just arbitrarily, the chemists who work on electrochemistry, they've arbitrarily said, we're going to call hydrogen 0 anything that is a stronger oxidizing agent than H plus will be positive, and anything that is a weaker oxidizing agent will be negative. And to get the actual values, what they did is they built a hydrogen half cell. So here it is, H2 and H plus. And then they hooked it up to all the other cells. And then they measured the cell potential. And as it says here, when it was connected, when the other half cells were connected to the hydrogen half cell, if they were a stronger oxidizing agent than H plus, you got a positive value. And they could actually measure the voltage. So that's where all of the voltages come from on your table of relative strengths, is they were all hooked up to a hydrogen half cell. And then their voltage was measured, the positive or negative, and the amount. This is an interesting half cell. It needs to have a gas tube because we're bubbling in hydrogen gas. And then we also have acidic H plus ions. So that is our half cell right there. Okay, so this is hydrogen as the standard half cell that all other half cells are compared to. Now, for some reason, hydrogen isn't always going to be the standard. They vary it, they change it. So let's say, for example, that instead of hydrogen, we're going to use zinc as the new standard reference half cell. So that means all the values in the table are going to change, because we now say that zinc 2 plus gains 2 electrons and goes to zinc, and its cell potential is now 0. Okay, how did it get to 0? Well, here we are at negative 0.76. This is now the new half cell. So how do we get that to 0? We have to add 0.76 volts to get it to 0. Okay? So if you want to see the math on that, negative 0.76 volts plus 0.76 volts gets us to 0. Now, what does that do to every value in this table? That means that all of them have gained 0.76 volts. They've all been shifted by positive 0.76. So what does that mean? What is the new cell potential of the Fe2 plus half cell? Okay, so here's Fe2 plus. Well, it was negative 0.45. It's gained 0.76. So that is now 0.31 positive. That's its new value. Hope I did the math right on that. You can figure it out on your calculator if you want to double check it for me. Second question, what is the new cell potential for the copper 2 plus half cell? Okay, copper 2 plus is here. So it was at positive 0.34. We're adding 0.76. So that would be its new cell potential. I'm just going to color code these in green. So that's the new one, and this is the new one for iron 2 plus, copper 2 plus, if we made zinc the new reference half cell. So it's no longer that, it's 0.00 volts. Okay, what if tin, we're changing it up here. Now we're switching to tin 2. What if tin 2 is the new reference half cell? Okay, well, tin 2 is right here. So how do we get that one to 0? We would have to add positive 0.14 volts. And that would give us 0. Okay, so if tin is the new reference half cell, what happens to iron 2 plus? Okay, iron 2 plus would now be its new value I'll put over here. We're adding 0.14 volts to negative 0.45, which becomes negative 0.31 volts. Okay, so iron 2 plus's new cell potential is negative 0.31 volts if tin is the new reference half cell. This is messy, but I hope that makes sense to you. Okay, hopefully that makes sense for you guys. Varying the reference half cell. We'll do one question together here. Okay, what if zinc was assigned a reference half cell value of 0? So we did this, kind of did this already. So this, to get it to 0, we have to add 0.76 volts. Okay, now it's at 0. All right, what would be the new cell potentials of hydrogen and copper? So hydrogen was at 0. It would now be positive 0.76 volts. And copper would be positive 1.10 volts. Okay, so there's copper's new value, there's hydrogen's new value, and there is zinc's new value. Calculate the overall cell potential for a copper zinc cell using their original values and those determined from part B above. Okay, so originally, electric cell potential is cathode minus anode. So using original values, cathode of copper would be 0.34 minus negative 0.76, positive 1.10 volts. Okay, that's original. And now we're going to go to the new reference half cell. And for the new one, cathode minus anode is, let's switch up the colors here, 1.10 volts minus 0.0 volts, which is, okay. Why is it the same? Why is it the same? Well, if we change both half cells by the same amount, their difference doesn't change. Hopefully that makes sense to you. This difference is 1.10 volts. It doesn't matter if I add 0.76 to both of them, okay, or these two. I guess I wrote that wrong. It's hydrogen to copper, 1.10 volts. So it doesn't matter. If we add 0.76 to both, if we subtract 0.3 from both, we're doing it to both. Their overall difference does not change. So this is the trick question of the day. Half cell potentials change, overall cell potentials don't when you vary the reference half cell. And that's it, ladies and gentlemen. So there's just a couple questions to do in your textbook. And I think there was one question on here you might have struggled with yesterday. And that was, just taking a look at it here, varying the reference half cell number 4. Yeah, 4 is a little tricky. So maybe it's not 4. I lied. It's number one. Number one is varying the reference half cell. So you can go back and try number one in your study guide on page 269 if you would like practice on that skill. And you've got your lab to do, which is only going to take you about 10 minutes to fill in those values in the table and then test them with the actual battery in a light flashlight and get those values and see how your predicted values compared to the actual values that you got in the lab. Okay, hopefully that goes well for you guys. And tomorrow you'll be getting your review assignment, review a quiz on these 3 days of material.